Hi everyone, we are Group 70 and today we are presenting our work on image captioning using CNN-LSTM as part of our neural nets and deep learning course. This project is motivated by real-world accessibility issues, how visually impaired users access and understand visual content. Our motivation. Let's start with motivation. Many websites lack proper alternate text images, which is critical for screen readers. Manual writing captioning is tedious and inconsistent, especially at a large scale. Existing models often miss context, object, relation, or human interaction cues. Our goal was to build a model that generates better captioning using CNN and LSTM, which makes web more accessible. Coming on to inputs and outputs, our input is an image from Flickr 8K dataset, which includes real-world scenes from people, animals, and objects. We use efficient net to convert each image into 1280 dimensional feature vectors. The LSTM decoder then generates captions word by word based on this vector and the previous words in the sequence. Now moving on to methodology, which will be carried on by my teammate Om.
Hi everyone. So this is our methodology, and we have improved a lot from our baseline model. So as you could see, we have introduced something here called as gate mechanism. So starting from the first, so we have our image and captions, and these go to our CNN model for image extraction, is for the feature extraction. Earlier, we were using VGG16 models, but upon peer evaluation on Twitter, we were told or we were said that EfficientNet or Mobile ResNet are some better models. So we shifted to EfficientNet. And then we have here something called as gate mechanism. So like for each input vector, the gate mechanism computes a scalar value between 0 to 1, and this determines the power of whether the LSTM should process those input features or not. So what actually gate mechanism is, we have taken this reference from called as adaptive computation layer. So what is adaptive computation is that it saves computation by skipping unnecessary steps for easy input, and then we can focus on complex inputs. So this saves our time both during the training part and also during the inference time when the model is training. Also, we have improved our data pipeline. So we have now included caching. So the same images don't have to again work again and again. And we have also used parallel processing. So our GPU is constantly fed with information. So after gate mechanism, the gate this we have a threshold, so it skips if the value is very low, and if it requires, then it runs and then it combines the output. Moving on next, uh, this is our optimization. So this is the one where we take our inspiration from. So as you could see, the figure A is the base one, which uses full LSTM power, and figure C is the adaptive one, which you computes a score from 0 to 1. Again, the next slide. So these are the metrics that we have used. We have used Blue, Meteor, Rogue One, and Rogue L. So it's pretty decent compared to what we were getting out on our baseline model. And we are using Flickr 8K dataset. Again, the next one. The main thing that we have improved from the baseline model is the average time per epoch. As you could see, we were having 4 minutes to train one epoch, but as you can see in optimized model, we are taking less than 40 to 50 seconds to train a model, so which is excellent on those epochs. So now we will be having results which will be told by Avik.
Moving on to results. So here you can see that there's a dog and the water behind, and two human beings are sitting on the dog, and this is the basically expected outcome. Now, what our model generated? Our model said that a man and woman sitting in front of a pool. It is imperfect because it's not able to detect water yet. Moving on to the next result. So here we can see that there's a garden, a lake, and two persons are standing on the side of that lake. Now, what our model predicted? Our model predicted two children at an edge of a lake facing the water. Now, moving on to the third result. This is a boy wearing a blue shirt, and we can see that behind him there's another boy who is playing joyfully on a beach, on a shore, and that is the expected outcome. Now, what our model predicted? Our model predicted boy smiles for camera, by his arms are stretched out and on the beach, which is kind of perfect. Now, we know that our models are not that perfect, and it contains some kind of imperfectness. And why this is because we used Flickr 8 data set, 8K data set, which is basically 8,000 images. Now, if we would have used Flickr 30K dataset, which is 30,000 images, we would have yield more better results. But that comes with a challenge. That dataset requires more computational power, more resources, and more training time. So I feel that, and my group feels that, whatever images are generated and the captions are generated by our model are optimal, and people can get better understanding by seeing those captions. These are the references that we have used. Thank you for listening to us.